Okay, so now we're going to go into chapter 19, chapter 19. What in the world is Titan? Chapter 19, which is all about turbulent boundary layers. And there is a very wonderful and at the same time very kind of frustrating thing here, which is simply that we don't know anything yet. I won't say anything. We just don't know much. Like, there is no perfect equation for this. We don't have some perfect way of modeling it. Like, there's this guy, let's see here. So, Arnold Sommerfeld. And he was really big in the 1920s. He's this big German physicist. And he had two hopes in his life. Okay, two hopes. Those hopes were, one, to understand the quantum realm. Like, what is quantum physics, And two, to understand turbulence. By the time he died, quantum physics, guess what? We had kind of gotten really close there. We weren't completely there yet, but we're closer. Turbulence, not a chance. Not a chance. Okay, so I'll give you the big overview which is simply that nature always moves to disorder. This is the second law of thermo. Second law of thermo simply says that my change in entropy, which is chaos, a measure of disorder, is always more than or equal to 0 for any process. Always, every single time, always. So we will go from laminar eventually to turbulent, because turbulent has more disorder, turbulent has more chaos. Okay, so what happens when I go from laminar to turbulent? We'll compare them. So here's my wing, here is the laminar boundary layer, here is the turbulent boundary layer. Okay, so first off, size. So for a laminar boundary layer, probably should have written that there we go. And here we got turbulent. Perfect. So size, laminar boundary layers are small. And comparatively, turbulent boundary layers are large. Okay. Now, let's see here. What about skin friction? Because we care about that. So CF. Well, in comparison, my skin friction for a turbulent boundary layer is large. And for a laminar boundary layer is small. And for heating at the wall, well, for a laminar boundary layer, this is small. And for a turbulent boundary layer, this is large. And then I'm just going to say, like, energy, okay? Energy. But here's where the things kind of, all what's been bad so far. Energy of a laminar boundary layer is small, but the energy of a turbulent boundary layer is quite large. And in this case, I'm just simply saying this helps it stay attached. So there is some good to having a turbulent boundary layer. So everything is bigger when you go from a laminar to a turbulent boundary layer. Everything is bigger. Now, sadly, there is no perfect theoretical model. Okay, theoretical model. For laminar boundary layers, we had some nice self-similar solutions for particular cases. We could say, this is how it will work exactly. We don't have that. So instead of having theory, like for laminar, we go to theory first. And then from that, we might go and check that with experiment. Turbulent, we can't do that. We have to go straight just to empirical theory. So we're going straight to empirical. So we use things that have been developed in the past based on experiment to understand what's going on. And just so you know, like, yes, there is no perfect theoretical model. We do have models for turbulence, it's just that they don't work perfectly. You could think about turbulence in the same way that people talk about gravity and quantum physics. So, you know, turbulence, like small scale and big scale. Okay. Like gravity is great at telling how things work at big scales, but not so good at small scales. Quantum physics is amazing at saying how things work at small scales, but not at big scales. And we're still looking for this unified theory. Like we're looking for a way of combining these. Okay? If we can find a way to combine it, it will be great. We just have not gotten there yet. Okay? And so the same way, for turbulence, we have models that do really well in big. We have models that do really well in small. We don't have one that does well everywhere and kind of giving us the features we should be seeing. We're looking for a way to combine those and find this perfect theory. And we're just not there yet, okay? And we might never get there. It might be something that is completely unmodelable. Okay, so I'm just going to give you two things, and then we're going to start applying them in problems. So from last time, we got various equations. We had, for boundary layer, we had the momentum thickness, we had the boundary layer thickness, we had the displacement thickness. There's all these equations. I didn't give all of them to you, but the two ones we did focus on was the skin friction coefficient and the boundary layer thickness. And so for turbulent boundary layers, we have those too. So for turbulent boundary layers, I have an empirical model that simply says that my boundary layer thickness is equal to 0.37x over my Reynolds number to the fifth power, okay? So that is the first one. Okay. And the second one is simply my skin friction coefficient, which is going to say that it's equal to 0.074 over my Reynolds number, this time base C, to the fifth power. This one's based on the chord, this is based on my position in the x direction. The reason it's based on the chord is that this is the overall skin friction coefficient, not the individual, like at that point, skin friction coefficient. Okay, that's why it's a C there and an X there. Be careful about that. Okay, and that's it. That's literally, we did it. Woo! The chapter is done. Nice. There's a little bit more about the reference temperature method, which I'm not going to worry about too much. So, because I can't just leave you there, we're going to do some problems. I'm going to show you some various examples. Now, it's applying the massive amount of information I gave you in this chapter into some problems. It's just how it is, okay? It's just how it is.